Welcome again. Today I will discuss silicon and lead based reagents in organic synthesis, and if you see the periodic table, so this is the right side of the periodic table. So this is 3A, 4A, 5A, 6A. So silicon is here and silicon is metalloid. And silicon and lead both are in the same series along with carbon. So this is lead, and lead is, this is metal, this is post transition metal. So in the silicon based reagents in organic synthesis, we will first discuss nucleophilic substitution reactions. Then we will discuss Peterson olefination, and in Peterson olefination there is basic elimination. Then we will discuss acidic elimination and protecting groups for alcohols. These are the silyl chlorides and deprotection also, deprotection for silicon based protecting groups with A minus. We will see different fluoride sources, and synthetic applications of silyl protecting groups, that also we will discuss, and protecting groups for alkynes, that also we will discuss. So now first we will discuss silicon based reagents in organic synthesis. So as we have seen, both silicon and carbon have similarity in having valency of 4 and formation of tetrahedral compounds. Regarding the differences, carbon forms many stable trigonal and linear compounds having pi bonds, while silicon forms few. So this is very important difference. This is because of the strength of the silicon oxygen sigma bond 368 kilojoule mole minus 1. So this is very high. The silicon oxygen bond is very strong, as well as the relative weakness of the silicon silicon bond. So silicon silicon bond is very weak, only 230 kilojoule mole minus 1. Most organic silicon compounds are similar to the ordinary organic compounds, being colorless, flammable, hydrophobic and stable to air. So they are colorless, flammable and stable to air, but hydrophobic. So we will discuss first nucleophilic substitution reactions of silicon. A nucleophilic substitution reaction at silicon differs in comparison to carbon compounds. So this is very important, that nucleophilic substitution at silicon and carbon are defined. Trimethyl silyl chloride, for example, does not react via SN1 pathway. So this is trimethyl silyl chloride. Which is similar with the analogous carbon compound tertiary butyl chloride. So this is tertiary butyl chloride. When displace silicon with carbon, you get this chloride. This tertiary butyl chloride. So this reacts in SN1, that we all know, but this will react in SN2. This is because the SN2 reaction at silicon is too good. Suppose this is the tertiary butyl chloride, and with SN1 pathway first the carbocation will form, and this is tertiary carbocation we know, and that is stable, and for that only this process is quite fast, and after that the nucleophile or anion like X minus here will attack and you get the product. So this is stable tertiary butyl carbocation intermediate. On the other hand, when this is tetrasubstituted carbon, this halide does not react by SN2. This we know unfavorable because of steric and electronic factor. On the other hand, for silicon like this trimethyl silyl chloride, this can react in SN2 fashion, and this is an important because silicon negative charge it can take and it is pentacoordinate. pentacoordinate. So 5 substituents are here around silicon, and silicon has a negative charge, and this is very favorable pathway. And after elimination of Cl minus, you get this product. So this is very important. And SN1 pathway, that is the silyl cation. Silyl cation, like this way, it does not occur because this is very favorable SN2 pathway. So this is very important. The tertiary butyl chloride reacts via SN pathway, whereas trimethyl silyl chloride reacts in SN2 pathway. Alkyl halides are soft electrophiles, but silyl halides are hard electrophiles. So this difference also we will see. The base nucleophiles for saturated carbon are neutral or based on elements down the periodic table. So this is important because alkyl halides, they are soft electrophile and soft nucleophile only react. So what is the soft nucleophile? Like OH, SH, I minus, Br minus, they are soft nucleophile. Whereas the base nucleophiles to silicon are charged or based on highly electronegative atoms like O minus, N minus, or NH minus, like this. So they are hard nucleophile because silyl halides are hard electrophile. So hard nucleophiles only react with silyl halides. The reaction of enolates at carbon with alkyl halides, but at oxygen with silyl chloride. So this is important. The reaction of enolates, that we know that at carbon with alkyl halides at the carbon center, but with oxygen it happens at the oxygen atom. So this is the enolate. And enolate we know that this is hard nucleophile because this is electronegative atom and this one is soft. So when the reaction happens with Rx, the SN2 reaction, the reaction will happen at the carbon atom on the enolate. On the other hand, when enolate reacts with silyl chloride, because this is a hard electrophile and this O minus is the hard nucleophile. So the reaction will happen at the O minus and O minus will react at this silicon and X minus will be leaving group and you get this enolsilane. So this is very important, the generation of enolsilane, because this compound enolate can be generated from cyclohexanone here with a base like triethylamine. So you can get the enolate and then react with trimethyl silyl chloride, suppose you get the enolsilane, and this enolsilanes can be used as nucleophile. Suppose in Mukayama Aldol-Michael reaction, So this chemistry is very well known, the enolsilane chemistry. And this is because the O minus it is reacting with silicon, because O minus is the hard nucleophile and trimethyl silyl chloride is hard electrophile. The SN2 reaction carbon is not much affected by partial positive charge plus on the carbon atom. So this is also important. And the SN2 reaction at silicon is affected by the charge on silicon. So SN2 reaction is at carbon is not much affected by the partial positive charge, whereas in silicon it is much affected. The most electrophilic silyl triplets react 109 times much faster with oxygen nucleophiles than silyl chlorides. So silyl chloride to silyl triplet, this can react 109 times faster. Suppose an example is acetal formation with Me3SiO triplet. Suppose if you react benzaldehyde with trimethyl triflate, first this oxygen reacts with silicon, because this formation is always fast, this energy is strong here, and now this oxonium ion is generated, oxonium ion, and now methanol will react to generate this, and again this arrow will be from here. This oxygen will react with another molecule of trimethyl triflate to do a reaction and to generate a oxygen plus charge here like this intermediate, and then again an oxonium ion will generate with a methoxy 1 after the elimination of this Me3SiO SiMe3. So, this methoxy will form a double bond here and this will eliminate, you get this oxonium ion again, and then methanol will react to generate this acetal. So, this is very important that SN2 reaction at carbon is not much affected by the charge, whereas SN2 reaction at silicon is much affected by the charge. As we have seen, this chloride is replaced by triflate, the reaction rate is much faster. For example, this acetal formation reaction. Peterson olefination is another reaction with silicon. The Peterson olefination is considered to be the silicon variation of the Huttig type reactions. The Peterson olefination is the reaction of an alpha silyl carbanion with an aldehyde or ketone to afford the beta hydroxysilyl intermediates that can be treated with either acid or base to afford the desired olefins stereoselectively. So, this beta hydroxysilyl intermediate will be formed, and that you can react with either acid or base to generate the olefin. An important feature of the Peterson olefination is that both E and Z isomers can be obtained from a single diastereomer. So, this is also important because acid and base cases two different mechanism operates and you can get both two defined olefins. So, that is very important. One advantage of the Peterson olefination is that the disiloxane RSiOH byproduct is usually volatile and thus readily removed in comparison to the involatile triphenyl phosphine oxide byproduct of the Huttig reaction. So, this is also important. We know that triphenyl phosphine oxide is solid and it is very difficult to separate in the Huttig reaction. On the other hand, this in the Peterson olefination, the disiloxane, that is usually volatile and that can be easily removed. So, we will see the Peterson olefination along with the comparison of Huttig type olefinations. So, this one is nucleophile and this is the carbonyl compound, carbonyl here, it is electrophile, and after this reaction you get this beta hydroxy compound with X here, and this can cyclize also as you have seen in the Huttig reaction, and after that you get this olefin. So, this is the main reaction, olefin is formed and XO minus is the byproduct. So, X is equal to PR3. So, here generally anion will be there, X is equal to PR3, that is Huttig reaction, X is equal to POOR2. So, this one that is Horner Huttig, and POOR2 OR2 that we have seen, that is the Waddsworth-Emmons, or we call Horner Waddsworth-Emmons reaction. X is equal to sulfur containing, then that is called Joule olefination, we have already studied, and today we will study X is equal to silicon containing, that is the Peterson olefination. So, what is the mechanism? First the basic elimination, basic condition we will see what is the reaction mechanism. So, this is basic condition, because that beta hydroxysilyl intermediate can be treated with either base or acid. The addition of the carbanion to the carbonyl compound, step 1, followed by the rapid formation of O silicon bond and elimination of the Synanon group. So, this is the reaction will happen here. This is the betaine intermediate, you can see. In some cases Elimination of the synanol is so rapid that no rotation about the CC bond is observed during step 2 and step 3, giving the same outcome as a concerted elimination from the betaine. So, this process here you can see in the anion, when its base is there, then O minus, this anion will react with silicon, and this O silicon bond will form, as you can see here, and there will be carbanion. And that is why they are telling this process will be very fast. So, the rotation along carbon-carbon does not happen, and after elimination you see this R1, R3 here also in the betaine, they are in the same site, and here also they are in the same site. So, this is called syn elimination. Also in the base, this also can happen that oxosilicate also can form when oxygen reacts with silicon. Without this carbanion, this also a possible like Huttig reaction, and here also R1, R3 are in the same side, and this after elimination like this way R3 SiOH will eliminate and you get this olefin. So, this also syn elimination. So, the action of base upon a beta hydroxysilane results in a concerted syn elimination step 2 or step 2a to form the desired alkene. So, whatever either step 2 or step 2a both will give you the syn elimination product. In the acidic elimination, the treatment of the beta hydroxysilane with acid results in protonation and in an anti-elimination to form the desired alkene. So, in the case of acid, the anti-elimination will happen. Suppose this beta hydroxysilyl intermediate, here because there is no acid, so this betaine will not form, also this silyl transfer will not happen because O minus is now OH, and in presence of acid this OH will be protonated. Instead of a transfer, OH will be protonated to generate this, so that it can eliminate as water. So, with acid this gets protonated and the acid conjugate base will attack to silicon and you get this one. So, here you can see they are both in the trans, and now R1 and R4 will be same side here because they are in this orientations same side R1, R4, and R2 and R3 will be same side. So, this is anti-elimination. Anti-elimination like E2 elimination, like E2 process. So, here the water is eliminated and minus SiR3 and conjugate base suppose Cb will be coordinated to silicon. So, this is a review, Chemical Society review 2002. Now, we will see some example. So, this reaction Peterson olefination can be also done in enantioselective fashion. Of course, if you get a chiral olefin, because if you have axial chiralities, though there is no chiral center, but if it is the molecule is axially chiral, then it can be a chiral compound. So, external chiral ligand mediated enantioselective Peterson reaction of alpha trimethyl silanyl acetate with substituted cyclohexanones. Like this one, this is substituted cyclohexanone. Cyclohexanone substituted cyclohexanone, and this is the silyl reagent. So, you have to generate an anion here with LDA. And now, if you put this ligand and if you see the structure of the ligand, so this anion will be chiral, will be in chiral environment, like we have seen in spartin. And now, this olefin will generate, and this is an axially chiral compound. Axially chiral compound, and this hydrogen can be down, CO2 ester, this is the ester motif, this can be in the top, and this work was published in Organic Letters 2002. So, in the Peterson olefination, if you generate the anion with LDA and then if you use ligand with like this ligand, two phenyl groups are anti each other with NMe2 oxygen methoxy, then the anion will be in the chiral environment and the product will be in the chiral. Suppose this syn anti elimination that can be understood when we use this beta hydroxysilyl intermediate. So, this is also beta hydroxysilyl intermediate. And now, if you put KH, potassium hydride, which is base, so what will happen? This product will form, because this syn elimination will happen, and as you can see in the molecule, they are in the same side. So, the syn elimination will give you trans product, because in this geometry they are in the trans. So, this will give trans product, and 96% yield with EZ stereoselectivity 95:5. So, trans product syn elimination. On the other hand, if you put acid like H2SO4, then what will happen? Then you have to give a rotation. So, this C3H7 SiMe3, then after rotation it will be C3H7OH. And now, in acid the anti-elimination, so anti-elimination will happen, anti-elimination, and this anti-elimination, as you have seen, this will be protonated like this, water will be eliminated, then you get the Z product. So, here Z is equal to 92:8, so Z is major. So, this is the cis product. Because in this orientation you can see they are in the same side. So, Z product will be major and the product yield is very high, 99%. So, these reactions are very efficient. Methylation of perfluoroalkyl ketones using a Peterson olefination approach also is possible. So, here the RF is this, RF is equal to CF3, CF2, CF3, CF2H like this, and if you treat with this silyl Gigner reagent, then you get beta hydroxysilyl. So, this is important. If you do Peterson olefination, then this beta hydroxysilyl compound or in intermediate you have to generate. This is the beta hydroxysilyl with this reagent in ether, room temperature 12 hours. And now, if you treat with TMSO triplet, TMSO triplet is a Lewis acid, even it is a strong Lewis acid. So, this is the acid mediated Peterson olefination in solvent, appropriate solvent, room temperature heating 15 minutes to 4.5 hours, you get this olefin. So, here also this elimination will happen. Because this is Lewis acid, this will react with the hydroxy and the elimination will happen. So, this is the olefin product is formed. It was published in JOC 2014. Z stereoselective aza Peterson olefinations with bis trimethylsilane reagents and sulfinyl imines. So, this is the bis trimethylsilane, 2 SiMe3 group is there, and this is the sulfinyl imine. This is sulfinyl imine. And with this sulfinyl imine and under basic condition, you can see here trimethylsilyl OK. So, this is base in THA minus 20 degree centigrade and ZE up to 95:5. So, Z is the major product. So, Z is formed. On the other hand, if you replace this sulfinyl side with phenyl, this is very interesting, same imine, but the substituent N substituent is defined. Earlier there was this one with sulfinyl group, now it is phenyl group, and under the same condition Me3SiOK tetrabutyl ammonium chloride THA minus 20 degree centigrade, you get EZ. E is measured here. E is measured in 99:1. So, this is very important. If you change the sulfonyl imine to N-phenyl imine, then the geometry of the olefin is changing. So, what could be the mechanism? So, the plausible transition state we can draw, and this is because if you see the structure of sulfonyl imine, there is a oxygen. So, this oxygen is important. This oxygen, we have earlier also seen that oxygen wants to make a bond with silicon, because that bond is quite strong, and that is why this takes this orientation like this, because this potential for O silicon activation, this wants to stay close to each other, this imine and this silyl, and this will give, because Ar and R in the close to each other, they are the seen. So, this olefin will be Z. So, this olefin will be Z. On the other hand, when R1 is equal to pH, that is the NPH, there is no oxygen. So, this will be trans to each other, these two groups. And now, if you see the orientation Ar and R in the trans, so this will give you E olefin. And this orientation is taking because of steric region also, steric region. And here the electronic region is operating. So, electronic region, electronic factor is operating, so that this potential for oxygen to silicon activation is possible, and that is giving Z product. So, this work was published in Organic Letter 2016. Now, we will discuss protecting groups for alcohols. So, silyl reagents have been used as protecting groups, that we will see, and this is very useful reagent. So, this trimethyl silyl chloride, and we will see other also tertiary butyl dimethyl silyl chloride, they have been developed by E.J. Corey, and after that this has been used as protecting groups for mainly for alcohols. Like trimethyl silyl, you can see this is the alcohol side, this is the silyl side. 3 methyl groups are present, and this called trimethyl silyl, ROTMS. Also, ethyl group can be present on the silyl, that is called triethyl silyl, ROTS. Also, tertiary butyl 1,2 methyl group can be present, that is called tertiary butyl dimethyl silyl, and that is called ROTBDMS or ROTBS, this also called. And tertiary butyl diphenyl, so this is diphenyl tertiary butyl diphenyl silyl, TBDPS. So, this is the ROTBDPS. And also their region is that the defined groups can be attached to silicon, then their difficulty in removal also. So, TBDPS, ROTBDPS will be much more stable than ROTBDMS, and this will be much more stable than ROTS, and this might be more stable than ROTMS. So, this is the stability. Now, how it is formed, the mechanism. So, ROH, R3, SiX, X will be chloride or triplet. Generally, they are commercially available, the silyl chlorides are triplet, and with appropriate base you can get ROSiA3. So, alcohol protection. So, this is the alcohol protection. Common bases that are used, like pyridine you can use, DMAP, sometimes combination of them, triethylamine DMAP, 2,6-luteridine, this is also strong base, and imidazole also used. So, base and silyl chloride or triplet can be used for the alcohol protection. Now, tertiary butyl dimethyl silyl ethers, TBDMS. So, this is the condition, alcohol TBDMS chloride with imidazole base, you get this ROTBS TBDMS. TBDMS. So these reactions are very easy to perform, and the mechanism here, it is that alcohol will react first with saline, and this chlorine will eliminate like this Cl minus, and you get a oxygen, there is a positive charge, and this H will be taken by the imidazole here to get this neutral compound RODMS plus imidazole HCl. So, because HCl is generated in this reaction, and to quench the HCl you have to use the base. So, base is required to quench the HCl, and also this base is helping here. From the oxygen positive charge, this hydrogen proton is taken up by the imidazole. Example, suppose if you have this allylic alcohol, chiral allylic alcohol with TBDMS chloride imidazole, you get this compound alcohol protection by the TBDMS group. It can be represented like this. Also, no disturbance of the chiral center. No disturbance of chiral center. So, this chiral center, this is not disturbed. So, this is very important, that in this reaction the chiral center is not disturbed. Also, if you have a secondary alcohol and primary alcohol, then the primary alcohol will be reacted selectively with TBDMS chloride. This is because of the steric region. Because the silyl groups are quite steric, so with TBDMS chloride imidazole maybe at low temperature, you can selectively protect the primary alcohol. Deprotection of silicon based protecting groups. So, one of the major rule for the good protecting group, that it should be easily protected, also it can be easily deprotected, then only it is a good protecting group. And this also follows in these cases, and generally fluoride sources are used for the deprotection of the silyl ethers like tetrabutyl ammonium fluoride, which is TBAF. This is commercially available either as solid or THF solution. Also pyridine HF can be used, this is mild, this also mild, and hydrofluoric acid, this is not mild, this is strong condition. So, you have to be careful with hydrofluoric acid. These are solution in water, 40% HF, 30% HF like this available, and ammonium fluoride also can be used, NH4 plus M minus. So, what is the mechanism? The mechanism is that M minus here reacts with silicon. So, like oxygen has a good reactivity for silicon, and M minus also has a good reactivity, because M minus, if you see the size, so this is because of small size, it is a hard nucleophile. And because this M minus is hard nucleophile, like O minus, it can react with silicon and will generate this. The silicon has a negative charge, plus H plus is formed, and after elimination of this RO minus, you get this triethylsilyl fluoride. So, this is the byproduct, and after aqueous workup, you get the alcohol. So, you can use different fluorides for the deprotection of silyl ethers, and these fluorides are commercially available, and this deprotection can be easily performed. That is why the silyl protection is a popular method in organic synthesis. Synthetic applications of silyl protecting groups. The bulkiness of TBDMS and TBDPS ether protecting groups can be used to advantage to suppress hydrogen bonding to the oxygen, restricting any incoming reagents to approach from the least hindered side of the molecule. So, this is also important because silyl groups are bulky, so they can also affect. Like this allylic alcohol, if you do reaction with MCPBA, this M will be small, metachloroparbangic acid, that is the epoxidation. So, electrophilic epoxidation with MCPBA, and this hydroxy is directing. So, hydroxy directed. So, this one is hydroxy directed because this hydroxy group react with the MCPBA, and that is why it is coming from the same side of the hydroxy group. So, epoxide is coming from the top side because hydroxy is the top side. So, the top side attack, and that is the hydroxide directed. And now, if you protect this OH group with TBDMS chloride, if you treat and imidazole, then you get this TBDMS, and this can be treated with MCPBA. So, this is very important. When you put MCPBA, steric region, mainly for the steric region, and because this silyl group is there, that is not allowing MCPBA to interact with this oxygen. Here oxygen is free, here it is protected. So, MCPBA cannot interact with this oxygen atom. So, the direction is not there. So, now what is the direction? Because this group is now sterically big. So, this is sterically big. So, the MCPBA now coming from the downside, and you get this down epoxide, and this TBDMS group can be deprotected with TBAP. So, you get this compound. As you can see, this and this, they are diastomers to each other. So, this is very important. The allylic alcohol, if you treat with MCPBA, then the hydroxy group is directing the epoxidation, you can get from the same side. On the other hand, if the alcohol is protected with TBS group, then this direction will not be operating, only the steric effect will operate, and that case the MCPBA will come from the opposite side of the OTBS group, and you get the other diastomer. The bulkiness of TBDMS and TBS group, ether protecting group, can also be exploited in incorporating the protecting group on less sterically encumbered primary hydroxyl groups selectively using submolar amounts of the silyl chloride. Like here, secondary alcohol, primary alcohol is there. How to convert to the ketone? So, though we know that some oxidizing reagent can do this oxidation, but you can do it silyl protecting groups also, and here you can selectively protect the primary alcohol to generate this OTBDMS, and PCC oxidation will generate this carbonyl compound, and TBF deprotection will generate this compound. So, this is a formal secondary oxidation over primary alcohol. So, primary is protected and then the secondary is oxidized. Also, protecting group for alkynes, this is also a good method. So, this hydrogen is acidic, with butyl lithium you get this lithium compound, and now it can be treated with Me3SiCls to get this alkalized silane, and if you treat this compound with butyl lithium, then this proton will be deprotonated, and you get this lithiated compound, which can be treated with other electrophiles to generate this compound. So, this is very important, because simply without this protection, if you want to treat N-butyl lithium, always these terminal alkynes will be deprotonated here. So, that way with silyl protection you can protect it, and then you can functionalize this carbon center. In the lead based reagents in organic synthesis, we will discuss reaction with alcohols, then reaction of 1,2-diols, cyclization of saturated alcohols, reactions of carboxylic acids, Cauchy reaction, acetoxylation reaction, and dehydrogenation reaction. Organolead compounds are chemical compounds containing a chemical bond between carbon and lead. The first organolead compound was hexaethyl dilead Pb2C2H5O6 synthesized in 1858, sharing the same group with carbon. Lead is tetravalent. Also, going down the carbon group CX, X is equal to carbon, silicon, germanium, tin lead bond becomes weaker and the bond length larger. The CB bond in tetramethyl lead is 222 picometer long with a dissociation energy plus 49 kilocalorie mole, 204 kilojoule per mole. The dominance of lead 4 in organolead chemistry is remarkable. By far the most important organolead compound is tetraethyl lead, formerly used as an anti-knocking agent. The most important lead reagents for introducing lead are lead tetraacetate. This also we will discuss, and use of organolaids is limited partly due to their toxicity. So, first we will discuss aryl lead triacetates. Their preparation, arene compounds react directly with lead tetraacetate to aryl lead compounds in an electrophilic aromatic substitution. For instance, anisole with lead tetraacetate forms paramethoxyphenyl lead triacetate in chloroform and dichloroacetic acid. So, this is the reaction for the generation of aryl lead triacetate. This is anisole reacting with lead tetraacetate, and this is the acid. After elimination of acetic acid, you get this compound aryl lead triacetate. So, this is para-selective. This was reviewed in organic synthesis. And now, what type of reaction it can do? The lead substituent in paramethoxyphenyl lead triacetate is displaced by carbon nucleophiles such as the phenol macetol exclusively at the aromatic ortho position. The reaction is insensitive to radical scavengers, and therefore, a free radical mechanism can be ruled out. The reaction mechanism is likely to involve nucleophilic displacement of an acetate group by the phenolic group to a diorganolead intermediate, which is some related reactions can be isolated. So, this is the reaction. You can see this is the compound macetol. When react with this paramethoxyl lead triacetate in presence of base 3-covalent pyridine, then this oxygen reacting with lead and one acetate of course will eliminate, you get this intermediate. And now, the Claisen type rearrangement will happen. The reaction depends on the electrophilicity, because this carbon is electrophilic. The rearrangement will happen like this way, and you get this is the lead diacetate is the byproduct, and this carbonyl group will be generated, and this aryl group will come here. So, this is the quaternary center is formed. So, this is very nice that the first oxygen reacting and then the Claisen type rearrangement. This was reviewed in pure applied chemistry. The nucleophile can also be carbanion of the beta dicarbonyl compound. The carbanion forms by proton abstraction of the acidic alpha proton by pyridine akin to Noble-Gel condensation. The intermediate displaces an acetate ligand to a diorganolead compound, and again these intermediates can be isolated with suitable reactants as unstable intermediates. So, this is the reaction that aryl lead triacetate with pyridine, and this is the beta dicarbonyl compound, The arylation happens here. So, you can see this proton is displaced by this. So, what could be the mechanism? So, this reaction is efficient 82% yield. So, what could be the mechanism? Now, pyridine of course generate a carbanion here, and then this reacts here, and this organolead compound is formed, diorganolead compound. Lead is connected to two carbon groups here, and now the reductive elimination, because here also the radical pathway does not operate. So, reductive elimination will happen and you get this diacetate and your compound. So, this is an efficient method. It was reviewed in Organic Synthesis 1990. One of the powerful common oxidizing reagents available with wide applications for organic synthesis. So, this is lead tetraacetate, and now we will discuss which is called Kriege reagent. The reagent is very toxic, hygroscopic and trans-brown due to lead dioxide formation on exposure to air. Therefore, the reagent is to be handled with extreme care in a chemical hood. It is typically stored with additional acetic acid and it can be prepared with this lead oxide and 4 acetic anhydride, then this lead tetraacetate is formed and this is the byproduct, and this byproduct again can be reacted with chlorine to generate this lead tetraacetate. Now, we will discuss different reaction of lead tetraacetate. There are many reactions. It can react with alcohol to carbonyl, reaction of 1,2-diols where the cleavage will happen, cyclization of saturated alcohols, reactions of carboxylic acids, Cauchy reaction, acetyloxylation and dehydrogenation. So, first we discuss reaction with alcohol. LTA oxidizes alcohol to aldehydes and ketones in the presence of pyridine at ambient temperature. The reactions are efficient and over oxidation to carboxylic acids are not observed. So, this is very important. For example, pentanol and cinnamyl alcohol can be oxidized to give aldehydes in the presence of pyridine with high yield. So, this is important, the oxidation stops at the aldehyde. So, suppose N-pentanol goes to pentanal in 70% yield, also cinnamyl alcohol goes to cinnamaldehyde in 91% yield. Now, we will discuss reaction of 1,2-diols. So, 1,2-diols oxidative cleavage is observed to give aldehydes, ketones or both depending on the structure of the diol. So, this is like sodium periodate oxidation, we have seen the oxidative cleavage. So, lead tetraacetate similarly cleave the diols. Reaction involves a cyclic intermediate and cis 1,2-diols exhibit greater reactivity compared to trans 1,2-diols. The reactions are performed in organic solvents such as benzene, toluene, dichloromethane and THF. When 3 or more hydroxyl groups are present on adjacent carbon atoms, then the middle one is converted into formic acid. So, this is also important. Like this diol, then this cleavage happens, you get 2 carbonyl compounds. Also, if you see this structure, there is a chiral OH here, O benzyl, and this one. So, this is the diol, this cleavage happens and you get this aldehyde and this chiral center is not disturbed. So, this is also very mild reaction. Also, this diol you can see cleave give this ketones and aldehyde. So, what could be the mechanism? Now, cis diols are cleaved more readily than trans diols. Defined mechanistic interpretations are thus proposed for these two processes. So, this is the cis diol, this is Decalin system. Cis diols reaction rate 1000. On the other hand, trans one the reaction rate only 1. So, trans diols very poor in this case. So, mechanism will be defined. So, what will happen with cis diols? The 2 molecule of acetic acid will eliminate, this 5-membered intermediate will form, and after that this cleavage will happen like this way, you get 2 carbonyl compound and lead diacetate. On the other hand, in trans cases, this kind of intermediate will form, this one, the OH reacting here to after elimination of acetic acid, this intermediate is formed, and now the anti-elimination will happen. So, like this way the cleavage will happen, you get 2 carbonyl compounds and this lead diacetate. The reaction condition can be used for the oxidative cleavage of the compounds such as beta-amine alcohols, 1,2-diamines, alpha hydroxycarbonil and 1,2-dicarbonil to give similar results. Like this alpha hydroxy ketone with lead tetraacetate ethanol, you get this ester here. This is aldehyde, but this is ester. And cyclization of saturated alcohols, this is also an important reaction that you can get cyclization if a delta hydrogen is there, undergoes cyclization in presence of LTA via radical pathway to give tetrahydrofuran along with low yield of tetrahydropyrans. So, this is alpha, beta, gamma, delta, then this cyclization happens to give the tetrahydrofuran. Here also alpha, beta, gamma, delta, now this OH reaction here and you get this bicycle. Also, you can see this kind of compound, there is a OH here and there alpha, beta, gamma, delta, this methyl group here, it is making a tetrahydrofuran with lead tetracid iodine and H mu. So, what is the mechanism? Now, this reaction of alcohols with LTA may give the intermediate A which can undergo. So, this intermediate will form, OH first react, and this can form a radical now. Instead, in presence of heating or light, the alkoxy radical B will be formed, and this alkoxy radical B will make a carbon radical by abstract of gamma hydrogen abstraction. So, this is very important, which may react with lead triacetate to generate this, and after, so this is D, this is C, and undergoes heterocyclic cleavage. So, then a carbocation is formed. So, this is important, radical and then carbocation, and then the cyclization will give the tetrahydrofuran. Reaction of carboxylic acid with LTA undergo decarboxylation to products such as esters, alkenes. So, this one cyclobutane carboxylic acid gives cyclobutene. Also, this dicarboxylic acid gives the olefin here. When a double bond is located nearby, lactone is obtained. Like this substrate, you can see there is a double bond with LTA, you get this cyclization, lactone ring is forming and with a acetoxy. So, what is the mechanism? So, mechanism will be that this carboxylic acid first react with lead tetraacetate to generate this, and then the bulky lead attacks 3, then this homolytic fission will happen, homolytic fission of the ester 2 give alkyl radical. So, this radical will form, and after this radical is formed, the lead tetraacetate will react to generate this intermediate 4, and it comes from the less hindered phase. Fragmentation of the latter or of the radical by oxidation would yield the tertiary carbonium ion 5 lead diacetate and acetate ions. So, this formation we have seen. Now, the elimination of lead diacetate and acetate anion will give this carbocation, and elimination of proton from either C16, C18 or C22 would then give rise to the alkene mixtures 6, while attack by acetate anion would then afford the tertiary acetate 7. So, if you see this 5, there are possibility of 3 olefin formation, because 3 beta hydrogen is there and 3 olefin formation is possible. So, that is the olefin mixture. So, olefin mixture 6, or the acetate anion which formed earlier can react with the carbocation to generate the tertiary acetate. Cauchy reaction is an organic reaction for the decarboxylation of carboxylic acid to alkyl halides with lead acetate and a lithium halide. So, this is the reaction, lead tetraacetate and lithium chloride, then you get the RCl. This is the example, this acid if you put lead tetraacetate, then you get this chloride, and these are the byproducts, carbon dioxide and acetic acid and this lead compound. And this reaction is a variation of Hunds-Dicke reaction where silver salts of carboxylic acid react with bromine carbon tetrachloride to get the RBr. Acetoxylation ketones undergo reaction with LTA to give acylated products at alpha position. The yield can be improved with catalytic amount of BF3. So, this is the reaction with lead tetraacetate, you get this alpha acetoxy carbonyl compound. Cyclic ketone as well as acyclic ketones can react. So, what will be the mechanism? Is the enol is formed, then this radical is formed. So, lead radical and this oxygen radical, then the acetoxy radical is formed, and then the acidoxy compound alpha acetoxy carbonyl is formed. Naphthalene and benzene derivatives having electron donating substituents could be acetylated on the thermal conditions, like this naphthalene can be reacted with lead tetraacetate, acetic acid heat, you get this acidoxy compound. In alkyl benzene, the acetylation takes place at the benzylic CH bond. So, this bond is activated. So, this might be radical pathway. And lead tetraacetate acetic acid, you get this group CH2AC. Dehydrogenation, Aliphatic amines readily undergo reaction with lead tetraacetate to give nitriles, while the reactions of N disubstituted hydrogens afford azo compounds. These reaction conditions are effective for the oxidation of 4,4-dihydroxyphenyl to afford diphenylquinone. So, amine giving here this nitrile. So, this dehydrogenation. So, this is the dehydrogenation pathway, and easily an amine can be converted to nitrile. Also, this compound 4,4-dihydroxybiphenyl with lead tetraacetate, you get this diphenylquinone. So, this is a very important reactions, and this was reviewed in Encyclopedia of Reagents for Organic Synthesis. So, first today we have seen the silyl group and difference in substitution reaction, and then we have seen their use as protecting groups, silyl protecting groups, and generally they are protected in presence of a base, and then can be deprotected easily with fluoride source. Then we have seen the Peterson elimination. Peterson elimination is very useful method for generation of cis and trans or syn or anti-olefins from the same diastereomer depending on the acid or basic conditions. In basic conditions, syn elimination happens, whereas in the acidic condition anti elimination happens. Then we have seen the lead compounds and lead trioxyaryl first the preparation, and then we have seen the usefulness of this reaction, that phenol compound generally the radical pathway does not operate in these cases, and phenol compound give this quaternary center carbonyl compound. So, carbonyl compound form with a quaternary center. Also, beta dicarbonyl compound can also be reacted, and the quaternary center can be formed, arylation at the quaternary center. Then we have seen the oxidation with lead tetraacetate. The lead tetraacetate is very useful reagent in organic chemistry. So, lead tetraacetate, it is called Kriege reagent also. So, lead tetraacetate we have seen first oxidation of alcohols, primary alcohol goes to aldehydes, selectively not over oxidation happens, cinamyl alcohol goes to cinnamaldehyde, then diol cleavage we have seen, and we have seen the syn diols react 1000 times much faster than trans diol. So, the mechanism is defined for syn diol, 5-membered intermediate is formed in diol. Then we have seen the reaction acetoxylation reaction with carbonyl compound, we have seen the alpha acetoxylation happens, and we have seen the decarboxylation of carboxylic acid like cyclobutane carboxylic acid with lead tetraacetate generates the olefin. Then we have seen the Cauchy condition. So, Cauchy condition is that if you treat with lithium chloride in the same condition, carboxylic acid, lead tetraacetate and lithium chloride, then you get the alkyl chloride. So, the carboxylic acid is getting decarboxylated like Hunsdiecker reaction, and a halide is coming. And lastly, we have seen dehydrogenations like amines converting to nitriles, and diols like the conjugated diols, they are converting to the dienones. Thank you.